All right, let's have a look at practice question set number 18. It says, this is on Lenz's law. It says, first question says, a magnet is dropped into an open copper tube as shown below. The magnet travels through the tube. This is exactly what we did in our demonstration class, right? We dropped a magnet through a copper tube, and what do we find happened? Well, it accelerated at a rate that was significantly less than 9.81 meters per second squared. You remember why? Remember why? Well, Faraday taught us that if we have a magnetic field and we move that magnetic field, it's going to generate an electric current. If I move a magnetic field relative to a wire, I'm going to generate an electric current. But then Oersted taught us that if we have an electric current, that's going to generate a magnetic field. So now we get the two magnetic fields. We got magnetic field number 1 that causes the current, and then we get magnetic field number 2 that's caused by the current. It's these two magnetic fields now, magnetic field number 1 and magnetic field number 2, that act together to, what's the big word here? They act together to oppose the motion. Not necessarily attract, not necessarily repel. They do whatever they got to do to oppose the motion of whatever it is that's moving. So let's look at the question here. It says, which of the following diagrams best shows the direction of the electron motion induced in the copper tube in the induced magnetic pole at the top of the tube? Let's deal with the induced magnetic pole first, because that's the easiest part. If we're going to oppose the motion, and the motion is downward, if we want to oppose that motion, then which way is the magnetic field going to point? In other words, what's the pole of the top of this, position 1? North or south? North or south? Right here, quick. It's going to be north, right? It's going to be north because a north pole repels north. Now remember, we're not necessarily looking for repelling, but if it's coming towards it, it has to be repelling. Bottom line is it has to oppose it. If we were pulling this magnet upwards like this, then we would have to have a south pole here to attract it to oppose the motion. But that's not what we're doing. We're pushing it downward where gravity is. So that's going to be a north, that's going to be a south. That leaves us with either A or B that are that's the correct answer. Now let's look at the direction of motion of the electrons in here. Which way does the magnetic field point inside the, well, for lack of a better term, we'll call this a solenoid or a coil of wire. Which way does the magnetic field point? Inside. From? So from south to north, right, from south to north. So we're going to stick our thumb, remember this is the coil rule where we're sticking our thumb in the direction of the magnetic field, fingers in the direction of the current. So thumb is going to point upwards, magnetic field is upwards, fingers in front of the coil. If this is my coil, my fingers are going to point in front of the coil to the left. So we're going to say the electric current is going this way, to the left in front, which means the answer for this question is A. Right? Does that make sense, Blake? Yeah, the answer is conservation of energy because everything is based on the opposing force, and the opposing force is based on conservation of energy. If it wasn't an opposing force, if it was a helping force, then we would be getting energy from nothing. So it is conservation of energy. Let me tell you a little, let me give you a little secret here, a little trick. Whenever you get a question that says, how do we explain this, the law of blank, I would say probably 3/4 of the time it's conservation of energy. So if you've got a guess on that question, whatever the question is, okay, if it says, which of the following conservation laws explains something, at least 3/4 of the time it's conservation of energy. Occasionally it'll be conservation of charge, right? Conservation of charge. But occasionally it could be something else, but most times it's going to be conservation of energy. If you got to guess energy. All right, next one. This is the last one, I think, wasn't it? Or was there 4? Just 3? In the apparatus illustrated below, coil 1 is suspended by an insulating string such that the coil can swing freely. Coil 2 is connected to a DC power supply. All right, so this is a good question. This requires us to do the coil rule to figure out the polarity of my solenoid, and then it becomes a magnet and does its thing relative to Lenz's law here. So let's figure out the polarity of this coil 2 first of all. We've got electrons going from the negative end to the positive end. That means up in the back, down in the front like this. Well, we can figure out the polarity of this now by saying, well, my fingers go down in the front, and my thumb will automatically point in the direction of the field, which is to the left. So that means my magnetic field points to the left here. which means that this is which pole? Magnetic field inside the coil points to the north. And right here it points away from the south, right? All right, if I'm moving it to the right, and I've got a north pole that's going to the right, then what's the polarity of this coil 1 going to be? Side Y is going to be, to oppose the motion, side 1 has to be north, and this has to be south. Now, if I was pulling this away, then side 1 or side Y would have to be south to attract it to oppose the motion. But that's not what's happening here. So that is north, and that is south. Let's see what the question is here. Which of the following statements describes what occurs when coil 2 is moved toward coil 1? The magnetic field at coil induced at Y is a north pole. Yes, so it's going to either be A or B. It's a north pole. And when coil 2 is moved toward coil 1, what happens to coil 1? Does it get attracted or repelled? Well, we've got a north pole and a north pole. They're going to get repelled. So coil 1, unless it was fixed, would move away from coil 2. So we're going to say it's going to be A. The answer is going to be A.